House quiz 2. No comments? He'll be up soon. Now, we have looked at the solubility of calcium carbonate in ammonium chloride solution, 1 molar. We started by recognizing that at the minimum, the solubility of calcium carbonate in the ammonium chloride solution must be greater than the water solubility of calcium carbonate, because ammonium ion attacks carbonate ion more effectively than does water. The ammonium ion is a much stronger acid than water. Now, ammonium ion is by no stretch of the imagination a stronger acid. We're making a comparison and a decision based on the comparison. Ammonium ion is a much stronger acid than water. Ka ammonium ion, 5.6 times 10 to the minus 10 versus Ka water, which is 1.8 times 10 to the minus 16. Which justifies the conclusion that we've already voiced. Calcium carbonate must be more soluble than the calcium in the ammonium chloride system. But for that equilibrium reaction, we calculated K, found it to be 7.2 times 10 to the minus 8. That's hardly a big number. So we now know that although calcium carbonate is more soluble in the ammonium chloride solution, it is not very soluble at all. Which I remind you, you have recognized by way of laboratory work in assignment 3. Because when you put together this solution, this solution with this solution, what happened? Don't remember? A number of you by now should have done this. You got a precipitated calcium carbonate. Why do I have quotes on this formula? Ammonium ion, carbonate ion react with each other to a large extent. So can I make pure ammonium carbonate? No way. But you can still go to chemical companies and buy a bottle which says ammonium carbonate. The label will say that, the formula will read this. And when you look at this bottle, its contents will look, I don't know, kind of cloudy, unusual. You'll see the inner walls of the bottle kind of caked up with stuff. I remind you, if you ever have chance to use this bottle of ammonium carbonate, not the solution, but the solid that you buy from the chemical manufacturer, don't take the lid off the bottle and take a deep breath over the bottle. Why not? Because the ammonia is going to percolate out of there and knock you flat. Because if I construct a principal species inventory for this, what do I get? What's my PSI for this system, beside water? Come on, chemistry students. Ammonium ion, I can put the AQ tag on there if I want. What else? Ammonia. And I can put the AQ tag on there if I want. What else?
Carbonate. Bicarb.
Yes. Is there a measurable molarity of carbonate in there? You betcha. But it's not a principal species relative to these three. What this stuff really is ammoniated ammonium hydrogen carbonate. That's what it is. Now then, this means, since I mix this with this, and this is rich in this, the system is rich in ammonium ion, and I get calcium carbonate, this is already screaming at me that calcium carbonate is not particularly soluble in a high molarity of ammonium ion, because this system contains a high molarity of ammonium ion. Now, based on our detailed analysis, taking advantage of what we labored at in Chapter 18, in order to give ourselves the tools to analyze a water solution system in detail for all the species which it may contain, whose existence depend on pH. We obtain, as it follows from the information we wrote on the board at the conclusion of our last gathering. Hydronium ion concentration, this, pH 6.92, solution ever so mildly acidic. Calcium ion concentration of this. Ammonia concentration of this. Why is the ammonia concentration greater than the calcium ion concentration? It's not substantially greater, but it's greater. Why? We talked about this last time.
Hydronium reacts with bicarb and with water?
Well, I want to know why the ammonia concentration is bigger than the calcium ion concentration. In this system, beside that equilibrium reaction, is there any other source of calcium ion? Be careful when you answer this.
No.
Yes, there is. What is the other source of calcium ion? This system also contain water? You know damn well it does. That's a solvent for the ammonium chloride solution. For expediency, I'm leaving off the tags, solids and AQs and all that stuff. Does equilibrium also exist in this system? You're damn right. Okay? This. Again. K this. Which, as we have already recognized, this K, a lot bigger than that K, tells us that this equilibrium is the primary source of calcium ion, AQ. But this also doesn't. Well, so far then, we've said there are two sources of calcium ion, and things presently stand, we've only got one source of ammonia recognized. That should mean the calcium ion molarity is bigger than the ammonia molarity, but that's not true. Because in this system, is there another source of ammonia? You're damn right. We talked about it last time. What is it? In fact, there are two other sources of ammonia. What are they? Ammonia, ion, and water. And K for this reaction is Ka ammonium ion, isn't it? What's Ka ammonium ion? 5.6 times 10 to the minus 10, isn't it? Is that a bigger K than that? That means this will produce ammonia more effectively than this will give us calcium ion. Hey, we're letting this stuff talk to us. And if you keep your mind on PSI, you can get this. Now, what was the other possible source of ammonia? Remember the gang-up factor? We argued that bicarb ion and ammonia can in fact react with each other in this system and produce quote-unquote hydrated CO2 and ammonia because of the gang-up factor. Now we know from an analytical standpoint this is a small extent acid-base reaction. But ammonium ion's in here at 1 molar. And the total bicarb molarity is pretty small, next to 1 molar. So we can expect some development of ammonia as a consequence of this reaction as well. So when we put these factors together, we know why the ammonia molarity is bigger than the calcium ion molarity. And why the bicarb molarity winds up being smaller than the ammonia molarity or the calcium ion molarity. And if we take it to determine the extent of the analysis to determine this, we get 9.7 times 10 to the minus 4. This corresponds to 22% conversion of carbonate initial to this. That's significant. What's carbonate initial? Is there a value for carbonate initial on the board? Yes, there is. What is it? Initially, how does carbonate get in this system? Calcium carbonate dissociates, doesn't it? And when the calcium ion goes into the system, calcium ion just sits there, doesn't it? So the calcium ion molarity is carbonate ion initial. There it is. So if you use that number in conjunction with this number, you can find out that this statement is true. Now, let's proceed with the experiment we said we were going to do. See if we can verify all this fancy arithmetic by experiment. Now, in doing a rush analysis of a topic that I've been meaning to include but have not yet included, specifically activity, I found out that activity is indeed very important and also an extremely large can of worms. That means there's a whole lot of stuff going on with activity, which, as far as research to date has... Donations? As far as research to date has demonstrated, a lot is not known about activity. But I have found out that activities of ions, or as I've written here, ion activity, activity of ion, depends mainly on ionic strength. Now tell me, for the analysis of this system, or for the system itself, what is the primary contributing factor to system ionic strength? Calcium carbonate saturated in the ammonium chloride solution. Which system components for this system contribute principally? What are the main causes? What are the main components of the system which establish ionic strength? I'm listening. You got any idea what ionic strength means? It's a measure of something that you did in Chemistry 2045 laboratory. You remember total ion concentration? You did? Good. I mean, I'm a dirty rat. I got this stuff going on in 45 so that at least some of you will come into this 46 class and have an idea what the hell's going on. I'm not going to have you in there monkeying around with stuff like Bohr hydrogen atoms. The hell with that. I mean it. From a practical standpoint, that stuff has no importance to students in first-year chemistry of consequence. Whereas water solution chemistry is arguably the most important chemistry in the whole daggone world, and that ain't going to change because we live in a water-solvent life system. And anybody who wants to argue with me about that, damn sure better get their guns out because I'm ready to shoot. My cannons are loaded. And I guarantee I'm going to win this fight every time. Which is why I tell these damn chemistry textbook authors, when they're monkeying around with all this analysis of quantum mechanics in a first-year book, they are stupid. Even the people who know a lot about this will tell you much of quantum mechanics is still in its foundling stages. They've done a hell of a lot of arithmetic. There's no question about that, because now we have wonderful tools called computers to do the arithmetic. But what does it mean? That's the part they don't know about yet. So me, being the kind of guy that I am, I like experimental chemistry in the main, because chemistry is unquestionably an experimental science. And I like chemistry to be made relevant to you folks. So where am I going? I'm going with water solution chemistry. So as a consequence of that, in 45L I have experiments purposely designed to get you ready for some of this stuff. Total ion concentration. A property of solutions containing ions, which you were asked to consider in 2045L, which leads in the main to ionic strength. So I ask again, for the system we are considering, what system components are the principal contributors to total ionic strength? I'm listening. The PSI will tell you ammonium ion and chloride ion. Aren't they the main ion components of this system? Hell, they're in there at 1 molar. Now the ammonium ion molarity gets reduced somewhat, but chloride ion molarity stays at 1 molar. So practically speaking, we're dealing with a solution whose total ionic strength is 2 molar. You agree with that? Because these other molarities of ions, they're not much at all. So I got about 1 molar ammonium ion and certainly 1 molar chloride ion. So I found something out. I think it's correct. Since a pH meter measures activity, I mean, how could a meter whose ability to react depends on ion concentration measure anything but? Yet I find the instruction manual for this thing, prepared by Fisher Scientific, tells me it measures concentration. This kind of stuff you run into in science. People who don't know what the hell they're doing. They're doing, but they don't know what the hell they're doing. How could this measure concentration directly? How could it do that? If I got ions traveling around as an ion pair, that's what this thing is going to measure. It can't do anything but. So, I have taken this thing and standardized it to a pH 7.00 standard. That part's taken care of. Now what I'm going to do, I need 1 beaker more for collecting wash. You people, and using, for example, pH meters in 46L, recognize that between readings you have to clean the electrode. You treat the electrode like a little baby's hind end, gently. What I'm going to do now is I've freshly made, last night, I know the label's too small, I should have made a bigger label, but I was here till after 7 o'clock rushing to get this done, and I was getting tired. 1.0 molar ammonium chloride solution. So I've got a clean beaker already containing a magnetic stir bar so that we're ready to get at this part of the experiment. And I put the electrode in the 1 molar ammonium chloride solution. It takes a while for the pH reading to stabilize. Now, who would like to be an observer? Just come up here, take some readings, report such to the class. If you're going to trust me, I'll be the observer. Okay. Now the pH is creeping down. I had it at 7.0. It's now at 5.36. It's going down, waiting for it to stabilize. All right. Now, while we're waiting for this to stabilize, I will tell you I did this last night, and I obtained a pH reading of, I think, 5.05 or something like that when it finally stabilized. Now, notice the directive up here. Let's get at this right now. Everybody. You can do this. This is easy. You accept this as being correct for our 1.0 molar ammonium chloride solution? Hey, with this kind of K value, whatever X is, it's certainly sufficiently small such that when you subtract it from M sub I, you're not changing M sub I. So there's a real tough calculation, isn't it? Hydronium ion concentration is the square root of this. Which is on the order 2.4 times 10 to minus 5. Now I want to cheat this. It was best 2 significant figure reliable pH reading. Anybody got a push button device? Take the square root of this thing and see what you get to 3 sig figs. I think it's 2.38, but in my rush, I didn't write it down. What'd you get, 2.37? Yes. Okay. Give me a pH for 2.37 times 10 to minus 5. 4.63? Correct, the 2 sig figs? 4.6 what? 4.63, 4.64, what'd you get? 4.63. All right. Now, interestingly enough, I read this very same solution last night. Same solution. Same setup, same gadgetry. I got 5.0, think what I say, 5.05, something like that. Now I'm looking at 5.20. But if my gee whiz analysis of this system is right, I don't give a damn. I'll tell you why I don't give a damn. We have recognized that for this system and for the system we're going to prepare when we put the calcium carbonate in there, total ion strength for the system is assuredly determined by ammonium ion and chloride ion. And when we put the calcium carbonate in there to saturate this, we're not going to change the ion strength very much, because not much ammonium ion will be consumed and no chloride ion will be consumed. So if this thing is reading, in fact, activities, and this number which I see is 5.20 is reflective of the activity, I can say that this difference in pH because if this thing was reading pH for the 1.0 molar ammonium chloride solution and reading it correctly, it'll read this. But it's not. It's reading this. Okay? So now when we put the calcium carbonate in there, since the total ionic strength is going to stay about the same, I'm going to get a pH reading for the ammonium chloride solution saturated with calcium carbonate, which is really a reflection of system activity rather than pH. How will I change the system pH? Am I going to get, when I put the calcium carbonate in here, am I going to get a meter reading which is too high or too low? Too high or too low? It's going to be too high or too low. Here's the meter reading. Here's what I should get. Is this reading too high or too low? Too high. Good. So whatever reading we get when I put the calcium carbonate in there, if I want to convert that to pH, I'm going to take the difference of these values and subtract it from that reading I get when I put the calcium carbonate in there. And that ought to give me a handle on pH. That's what I'm doing. I am, in essence, taking an activity and turning it into a pH by this gee whiz thing. On what basis? On the basis that the total ion concentration, the ionic strength of the system is going to be about the same as it is now as when I put the calcium carbonate in there. All right? Come on up here. Let's have a little... You're big and tall. You verify this reading?
Yes, sir.
Good. Talk to them, not me. Here goes the calcium carbonate. Now that's going to be more than enough. Tell them what's happening.
The pH is going up.
It sure as hell better, don't you think?
Yes.
Good. You can tell them it sure as hell better, don't you think? Go ahead. Now what we want to do, it takes a little bit of time, is for the reading obtained with the ammonium chloride solution, 1 molar saturated with calcium carbonate, we want the reading to stabilize. It takes a while. And in order to get this reading in a more time-efficient fashion, I have the system being stirred. Now the instructions for the pH meter that come from Fisher say, stir. Well, that's obvious. We should stir. So we're stirring. Okay? Now, who knows what's going to happen? I can tell you, when I did this last night, I wound up with a meter reading of 7.33. And lo and behold, when I made the correction, when I did this last night, I couldn't believe this one. I got 6.92. That's what I got last night. I said, this is too good to be true. Where are the students? We still going up?
Yes, sir.
Yeah. Where are we at?
We're at 7.18.
7.18. I'll put in a little bit more calcium carbonate. But I really don't want to put in too much, because I honestly have no idea what happens to the validity of the reading if some of the calcium carbonate adheres to the outer surface of the electrode. I don't know that it should matter, because the actual part of the electrode which does the reading is inside a perforated glass shield. So you can't really, by this, you can't harm the actual part of the electrode, the sensor part of the electrode, which is doing the reading. Where are we at now?
We're at 7.25.
Creeping up. Well, why don't you have a seat, because it's going to take a while. While we're waiting on this guy, we'll proceed to the next consideration. We'll now engage in rather a gee-whiz survey of most of the main considerations we have so far made in Chapter 19. We're going to do this by way of what's in the notes with what you see on page 1916. We're now at 729, still creeping. We're considering, with water being the solvent, saturated calcium hydroxide solution. Another semi-soluble salt of calcium ion, which you prepared in 46 laboratory and investigated some properties of. You did find, among other things, that if you're going to test successfully for calcium ion in a water solution, you wouldn't wish to do that by attempting to precipitate it as the hydroxide. Because precipitating it as the carbonate, since both require a basic precipitating environment, carbonate test is much more sensitive. Because calcium carbonate is a lot less soluble than calcium hydroxide.
Why do you have two sets of hydroxide?
Oh my. Bonus. Okay. To 1 sig fig, the pH of this saturated solution system is 12.6. So from that, if you wish, you can get the calcium ion molarity and the hydroxide ion molarity. To this system, we're now going to apply some changes and consider what will happen to the system as a consequence of the change applied. So we'll make a QPSI, a running QPSI inventory of the system as we apply the changes. Quantitative principal system inventory. Add 1 molar sodium hydroxide. Now, what you should also do on recognizing the impact of the change is to write the equation for the principal reaction which occurs as a consequence of the applied change. Well, let's make a little bit more room here. And here we'll write the reaction equation. What's going to happen when we do this? I mean, this, you know this. I'm upping this considerably, am I not? So what's going to happen to this? And as a consequence thereof, what happens to the amount of this? Increase, making more of this. Arrow up, increase, arrow down, decrease. So, the reaction which occurs is this reaction right to left. All right? Add 1 molar CaCl2. Up, down, increase. Same reaction. Add water with this qualifier added to it. The amount matters. Why does the amount matter? Pardon?
If there's enough, would the hydronium react with the hydroxide?
Hydronium?
Oh.
What hydronium? Oh, in the notes it says add HCl solution. I'm going to put that one next. My fault. I decided to throw this one in there first, before the add HCl. Add water. Now, let's imagine in our mind's eye. We got that system standing in this beaker. The system level is up here. In the bottom, you'll see undissolved calcium hydroxide crystals. Our system level's here. Now I'm adding water, stirring, adding water, stirring, adding water, stirring. As long as on adding water and stirring, I see calcium hydroxide remaining in the system. What can I say about the calcium ion and hydroxide ion concentrations?
They decrease.
They what? They stay the same. As long as calcium hydroxide is there, the equilibrium is preserved, is it not? That's the solvent. NC for no change. What happens to the amount of this? It's got to decrease. I'm dissolving more calcium hydroxide every time I add more water. So what reaction is occurring? I'm adding water. Calcium hydroxide is dissolving. But I see undissolved calcium hydroxide remaining in contact with the body proper of the system. That means the equilibrium is preserved. That's why the calcium ion and hydroxide ion molarities are so far remaining the same. But is a reaction occurring? Did more calcium hydroxide dissolve? Well then, damn it, a reaction is occurring. Left to right, but so far no delta in ions concentration. No ion concentration. Okay? Now, when I add sufficient water so that all the crystalline calcium hydroxide goes in the solution and proceed from that point to add more water, now I'm just diluting the calcium hydroxide solution. So now the molarities of calcium ion and hydroxide ion go down, and there's no longer a change in calcium hydroxide simply because there ain't no longer any calcium hydroxide. It's gone. So we'll do it this way. By the way, we're now at 732. All calcium hydroxide dissolved. Okay? Now, directive. This one's tricky. To try to help you recognize why this one is tricky, I'll draw a picture. This stuff, this chalk smear, represents undissolved calcium hydroxide crystals. Okay? I'm going to add some 1 molar HCl. Well, there's no question that hydronium ion attacks hydroxide ion quite effectively. So when I add the 1 molar HCl solution, hydroxide ion molarity's got to come down. The amount of calcium hydroxide's got to come down because hydronium ion is certainly going to attack calcium hydroxide. What's going to happen to calcium ion molarity? Increase. All right. Now let's imagine that I have added enough hydrochloric acid solution to dissolve half the original calcium hydroxide. So far, what reaction or reactions have occurred? Well, we really have talked about them, haven't we? Hydronium ion plus hydroxide ion and hydronium ion plus calcium hydroxide. These are each reactions different from either of the original system reactions, right to left or left to right. So I'd write and I'd write and this would be the main reaction of concern, because what we're really interested in is how the calcium hydroxide behaves in the system. All right? All right? Now then, with this, I will ask you a question. After dissolving half the original calcium hydroxide by treatment with the hydrochloric acid solution, what now will be the solution pH relative to what we started with? Okay? And what now will be the solubility of calcium hydroxide? When you think about that, we'll pick it up with that. the start of the next gathering. Our pH reading is stabilized at 7.33. So take the 7.33 value and let's see what we got here for a difference. 7, oh my. I'm afraid I will just wind this up by saying something was not correct. Something not correct here. Don't know what to say.